So today we're going to talk about the set of linearly independent vectors, how to check linear independence, and how we use this formulation to find solutions for Ax equals b. A lot of this will be in Julia because we want to look at the LU factorizations and we want to do solutions in a way that they're scalable. So, and then the rest of the recitation will look into plotting in Julia, and we'll go over some simple codes that help us get familiarized with how we use the plotting syntax. So, a set of linearly independent vectors. From previous recitations and in lectures, we've talked about this enough, so I'm just going to use the concise definition of linear independence. So if you were given a set V1, V2, V3 to Vm in a vector space Rn, so V1, V2, V3, Vm, they all belong to a vector space Rm. Then these vectors are linearly independent if this linear combination of these vectors always gives the zero vector. Now, our problem is to use this definition and let me zoom in. Yeah. Our problem here is to use this definition and check if this given set of vectors, so I want to check the given set of vectors v1, v2, v3, v1, v2, v3 that are in Rn. I want to check if these three vectors are actually linearly independent. So let's put them in our formulation. We get, let's assume alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 exists such that all of these add to zero, the zero vector. So if I was to write it down, I'd say alpha 1 times minus 1, 0, 0, plus alpha 2 times minus 1, 2, 0, plus alpha 3 times minus 2, 2 equals 0, 0, 0. What does this become? This becomes minus alpha 1 minus alpha 2 minus 2 alpha 3. This is 0, this is alpha 2 minus 2 alpha 3. This is 0, 0, 2 alpha 3 equals this. Now you will see these are sets of equations where all of the rows add up to zeros. So you can write this in Ax equals b format. And then this becomes minus 1, 0, 0, minus 1, 2, 0, minus 2, 2 times alpha 1, alpha 2, alpha 3 equals 0, 0, 0. We note that A is upper triangular. That was bad. So we can do backward substitution. If you do backward substitution, it is very easy to see that you'll get alpha 3 equals 0. And then the next equation is 2 alpha 2 minus alpha 3 equals 0, minus 2 alpha 3 equals 0, which gives you alpha 2 equals 0. And then from the third one also, you will very easily get alpha 1 equals 0. So we could prove that the only way that these vectors could satisfy this equation was if alpha 1, alpha 2, alpha 3 were 0, which means V1, V2, V3 are indeed linearly independent. We worked through examples like these in the previous recitation as well, so if you're still confused, this is a relatively simple example to start you off with, and then you can go into what we did last time. And so now that we've learned we've revised how to find if a set of vectors are linearly independent using the definition of linear independence, we move on to what we've been doing in class now. So we use what is called the pro tip for checking linear independence. So given a set of vectors v1, v2, vm, they are linearly independent if any of the following are true. It's just a rephrasing of the pro tip that you'll see in the book and in the lecture. So you can say that this set of vector is linearly independent if I define a matrix A, all of whose columns are given by the vectors v1, v2, vm. So matrix, if v1, v2, vm lie in the set Rn, I can conclude that the dimensions of A will be n cross m, where each column will come from the different m vectors from the set of vectors, and n will come from the length of each of those vectors, which is given by n. And how do we know that? We know that because we said that v1, v2, vm belong to the set Rn. So given all of this, once I've constructed an A matrix with all the columns given by the set of vectors, I can say that the set of vectors will be independent if the determinant of A transpose A is not equal to 0, or which also means A is invertible. But we know a better way to do it. We don't want to be doing determinants of really large matrices. We have a smarter way of doing that, which is using LU factorization. And then if you're using your LU factorization, you can say that the set of vectors or the columns of A are independent if, for any given LU factorization, I can say that the permutation matrix P times A transpose A, which will be an M cross M matrix, a square matrix, will be equal to LU of A transpose A. Once I have this formulation, I can look at the upper triangular matrix U, and if that matrix has no zeros on its diagonal, I can say that the columns of A are linearly independent. The proof of this is given in the books. It's also in your lecture notes, and if you want me to go over it, you can ask me in the office hours, or I can take it up next time. Let me know. So if we have this formulation, it doesn't make sense to sit down and compute LU by hand because it's tedious and it takes a little bit of a time. What we want to do is we just want to use the built-in Julia functionalities, observe our matrices, and then be able to make these conclusions. So this recitation, I'm just going to be using a lot of Julia. So if your problem was if you were given 3 sets of vectors, say this is V1, V2, V3, and I asked you if they were linearly independent, what you would do is you would stack them in an A matrix like this, and then you'll find out the LU factorization of A, get a U matrix right here, and then look at the diagonal elements of U. And if you find a 0 in there, means the sets are not linearly independent. And if there's no zeros in there, you know that the columns of A or different vectors are linearly independent. So let's see how you would do that in Julia. So I have this matrix typed out in Julia for us. And it is right here. So I'm going to be using random and linear algebra. So this is like a magic trick. What it does is it sets a seed in your random variables. So when you're sampling, it'll always give you the same distribution, and you'll end up getting the same numbers every time. But it depends on like when you set the seed, and you can look up the documentation of this. But the only purpose of using this here is so that I get this. I didn't want to generate these random numbers over here, like all these different values. So what I did was I just sampled randomly for this, and just to make it reproducible, I set a seed on my random variable so that I always get the same A matrix. So what this basically does is it creates an A matrix, which is given by this. It is equivalent to you sitting down and typing these things down. So let's see. So we have this, and I want to check if the columns of the A matrix are linearly independent. From our theory, we know that the way to do that is I want to get the LU factorization of A transpose A. So let's do that. I say LU of A equals LU of A. And then what you want to do is you don't care about what's in the P, you don't care about what's in the L, all you care about is what's in your U matrix. And not even the full matrix, you really only care about the diagonal. But let's, for our sake, just look at the U matrix for this formulation. So there you go. And because it's a pretty small matrix, and then A transpose A is just going to be a 3 cross 3, I can just look at the full matrix, and I can say, okay, the upper triangular matrix has no zeros in its diagonal, which means that when we translate it with our previous knowledge, I'm sorry, it had to be, A transpose times A. Yeah. And then you do that, yeah. Again, it has no zeros on its diagonal. So what it means is that how we translate it into what we already know is when you were looking at the determinant of A, or determinant of, in this case, A transpose A. We say that when there's no diagonals on it, when none of the diagonal elements on U are 0, that means that the matrix is invertible, or the determinant of that matrix is 0. So these two ways of checking our solution are actually equivalent, but we know that a better way to do it is not use the determinant, but to use the LU factorization. So that's what we did. And so we can report over here that columns of A are linearly independent, which is so much more easier than having to go through this one by one. And this is a lot harder to even do in Julia, because you'd essentially be solving for alpha 1, alpha 2, alpha 3, which is counterintuitive, and then you have to do forward substitution and then backward substitution. It's just so much longer. It's so much easier to just use the pro tip that we have, and that's why it's called a pro tip. So now let's see how that translates into a bigger problem. So the next part that I have here, again, I copied that down into Julia, and then when I run it, I get these numbers, this really, really big A matrix, and I'm going to create a cell down here. And what I'm going to do is, again, if I have to look at the LU factorization, I'll do this, but this time I probably, okay, let's see. It's going to be a really big matrix. Yeah, it's a 10 cross 10 matrix. It's really hard to see what's happening there. So what I do is I don't even care about all of U. All I care about is the diagonal elements of U, of this. And I also want to round the terms. I don't want to see the exponentials and everything. So I will just round off this matrix. And there you go. I get the diagonal elements rounded off to the first decimal place, and I get minus 28 and a couple of zeros down here. And that tells me that it is indeed that the columns of A are not linearly independent. And it's just as easy as that, just looking at the different diagonal elements in U. So here I can report from my Julia instructions, and I'll copy the whole working here so that you're not confused where to find these solutions and you don't have to go back and forth. But we can report that columns of A are not linearly independent. Easy. So if this is all clear, I am going to move on into how all of this relates to our solutions, that this problem that we've been working on finding solutions for a system of equations given as AX equals B. So we're going to talk about solutions of AX equals B and then break the problem down sequentially into, we'll first check if a solution exists. And then if a solution exists, what is the condition with which we can say that the solution is unique? So from our theory, we know that a system of equations, AX equals B, has a solution if B is a linear combination of the columns of A. Now, how is this intuitively understood? If I can write B as alpha 1 column of A plus alpha 2 second column of A to alpha m mth column of A, what I've essentially written down is that first column, second column, mth column, and this can be written down as alpha 1, alpha 2 to alpha m equals b1, b2, bm. This is essentially just A alpha or X equals B. So that means that if a solution exists, then B can indeed be written down as A times alpha. And intuition and all of that theory is in our lectures, and we can go over it. But if you were to just summarize that whole discussion, you can just say that the system of equation AX equals B has a solution simply if you can say that B is a linear combination of the columns of A. Now, given this, let's try and find out if the given system of equations indeed has a solution. So, if you're given these system of equations, we know how to write this in the form of AX equals B, where X will be A, B, C, and then B will be 20, minus 8, and 10. And then our A will become minus 1, 3, 5, minus 2, 0, minus 2, minus 3, 3, 4. So, I want you to prove that B is a linear combination of the columns of A, which means B, which is this, can be written down as alpha 1, the first column of A1. So let's first write that down. Let's write down for a solution to exist, we say B is equal to alpha 1 A1 column plus alpha 2 second column of A plus alpha 3 times third column of A. What does that mean when I write it down? It means 20 minus 8, 10 is alpha 1 times minus 1, minus 2, minus 3 plus alpha 2 times 3, 0, 3 plus alpha 3 times 5 minus 2, 4. Now that you have this, you can write this down as -1, -2, -3, 3, 0, 3, 5, -2, 4 times alpha 1, alpha 2, alpha 3. And then what if I gave you an LU factorization of this matrix? What if I can write it down as 1, 0, 0, 2, 1, 0, 3, 1, 1 times -1, 3, 5, 0, 6, -12, 0, 0, 1, give you the LU factorization with alpha 1, alpha 2, alpha 3. And then I'm gonna call this, you remember, a vector y, and then I say, well, 1, 0, 0, 2, 1, 0, 3, 1, 1 times y1, y2, y3 equals 20 minus 8 and 10. If you do the math here, you'll get y1 equals 20. Let me write it down better. You get y1 equals 20, then 2 times y1 plus y2 equals -8, and 3y1 plus y2 plus y3 equals 10. From there, I get y1 equals 20, y2 equals, was it 20? Okay, yeah, that was 20. y2 equals -48, and then y3 equals 60 minus 48 is 12 is -2, if I'm not wrong. Can't find it in my solutions right now. Okay. Let's see if that's correct. And then from there, I get -1, 3, 5, 0, 6, -12, 0, 0, 1 times alpha 1, alpha 2, alpha 3 equals 20 minus 48 and -2. And then from here, I can get alpha 3 equals -2, 6 alpha 2 minus 12, alpha 3 equals -48, and then -1 alpha 1 plus 3 alpha 2 plus 5 alpha 3 equals -20. And if you solve this, if I'm not wrong, you should not be getting that. It's probably 38, and I wrote it down wrong. That was 15. Let's see what this one gives us. So this one is -2. And this becomes +24, -48, +24. Wrong, this is -4. And then what does this one become? Alpha 1 is 20 minus, that's +10, 30, +12 is 42. I'll check that solution and I'll update it. But that's what I'm getting right now. And now that you've found a solution and you've written down B, if these values are correct, as alpha 1 times different columns of A, you can say that the system of equations has a solution. In fact, I think we actually found the solution. If you solve it, this is the solution. If you try and put it in these equations, hopefully it should fit. Let me try and do that. So, there's some calculation error, but that's what it should be. All right. Now that we know how to do it by hand, we've suffered through the solution. We know that there's a better way when we're working with linear combinations and linear independences. So to get to see if B can be indeed written as a linear combination of A, what we can do is we can see if all the columns of A, if the number of linearly independent columns in A and in the appended matrix AE, which is given as this, is the same, that means that B is a linear combination of the columns of A. Intuitively, why you can see that's true is that if A was written as different columns and so on, let's say that this had K linearly independent columns. These are K linearly independent vectors. If I add B to it, and B is linearly independent, if B was linearly independent, then this set A1 column, A2 column, AM column with B will have K plus 1 linearly independent columns. But if that is not true, that simply means that B is a linear combination of columns of A, which is what we needed, right? So now that we know that, now that we've seen why that intuitively makes sense, we know how to count the number of independent linearly independent columns in any matrix. And we do that using the LU factorization, getting the U vector, and then counting the number of linearly independent columns in that U matrix. And to count the number of linearly independent columns in any matrix, we have the semi-pro tip right here. So the semi-pro tip says, when we know the LU factorization for A transpose A, we can define that we define K to be the number of linearly independent columns of U. When K is equal, so we can say that we check this for linearly independent columns. When all the columns of A are linearly independent, we look at U and we get none of the elements on the diagonal to be zeros. And then we say, okay, all of the columns of K are linearly independent. So how many linearly independent columns are there? Well, there are M linearly independent columns in such a situation. All right. What happens if there is a zero element? Well, then you can say has one, exactly one. That is to be noted here. Exactly one zero element. So when there's exactly one zero element on the diagonal of A, you can say that there are M minus one linearly independent columns in A. Why is that? Well, that one column, wherever the zero is, that is the one that is like the linear combination of other columns of A, and that is why when you compose it, it becomes a diagonal element. Now, what happens when there's two or more zero elements? Then additional computations are necessary. For example, if the rows of U that have the zero in the diagonal element are identically zero, then K equals the number of non-zero elements on the diagonal of U. Lots of words. What that means is, in a case when there's more than, all of these are zero, and this is the diagonal. These are some elements, and all of this will be zero. If you get more than one zero on the diagonal, so let's say this is zero and this is zero, what you actually need to be just looking at is just this element. If this element is also zero, you're golden, and you don't have to do any additional computation. And you can conclude that there are M minus 2 linearly independent columns if this was full M cross M. So that's our semi-pro tip. This is how we count the number of linearly independent columns in A transpose A given an LU factorization. How we can put it to use is in checking the existence of solutions, where we want to check if B is a linear combination of A. So I count the number of linearly independent columns in A transpose A. If that's equal to the number of linearly independent columns in AE transpose AE of the appended A matrix, which we're going to look at from the U and the UE, then we're good. Then we've confirmed that there indeed exists a solution to the system of equations. So I've written down an example. This will be in like, if your x variable is just x1, x2, x3, and ax equals b, so if a is this and b is this, do you think a solution exists? Now, you have this. What you want to do is, I'm going to go to Julia, and I already have the numbers in there. So somehow, with the same magic, when I run this, I'm going to get that beautiful matrix, and I'm also going to get the right B matrix. And from there, what I do is I define an AE matrix to be A and concatenate the last column. So row-wise concatenation, where you add the different column to an A, and I create an AE matrix. I get the LU factorization of the A matrix, of the A transpose A. And I also get the LU factorization for the appended matrix. I get AE transpose times AE. Now I want to look at the diagonal, rounded off diagonal elements of the U matrix. Or let's not round them off just yet. Let's just look at them. And of the A and of the A dot U. And also for the appended matrix, I want to look at the diagonal elements of the U matrix. So let's see. So I get no zeros in the A matrix. So the number of linearly independent columns in the A matrix are 3. And the number of linearly independent columns in the appended matrix are 4. So this term is not 0. So it has more than the number of linearly independent columns. What does that tell us? Well, if U and UE don't have the same number of, so number of linearly independent columns of U were 3 and of UE were 4. These are not equal. So I can say that given system of equations do not have a solution. Which was easy, otherwise I would have sat down and tried to compute all these different things. But I know that a solution doesn't even exist. So let's try for an even bigger problem. So I'm gonna go back to Julia. I have another set of A and B, and let's see what happens for this one. For this one, again, I get my A matrix by some voodoo magic, get my B matrix by the same magic, and then we know what to do, we know what to look at. We want to get the appended matrix, we want to get the LU factorization of A transpose A, and the appended matrix is transpose multiplied by the matrix. And then you want to look at the diagonal elements of U. Now you see A has 7 linearly independent columns, and the appended matrix, well, there's a very small value in here. And one way to just remove that is just round it up. An element-wise rounding operation should help us, but this rounds up to like a bigger, I would set a precision I think I could set a precision. Let me see what this does. Equals 2. No, it doesn't. Oh, wait. So I can do this. Got it. Digits. Yeah, it's called digits. Yeah. So I rounded it up to 2 decimal places. And then I look at the elements, and well, as we expected, there's a 0 here. So the number of linearly independent columns in the appended matrix are 8 minus 1, which is 7, and there's 7 linearly independent columns in the normal A matrix. Because both are equal, we can say that B is a linear combination. So linearly, oh, my pen stopped working. Okay, linearly, number of linearly independent columns of U were 7 and of UE were 8 minus 1 equals 7, right? Thus, B is a linear combination of columns of A. AX equals B has a solution. I don't know how many, but there is a solution, which is what we got from our analysis. Very easily, might I add. So now that we know how to find out the existence of a solution in AX equals B, the next step is to find out, okay, so there is a solution. Is there only one solution, or are there an infinite number of solutions, right? Which is something we couldn't do with our previous determinant analysis, but we can do it now. So to get the uniqueness, we have an extra condition. So we say that B, for the existence, this is the condition for existence, and I say B is a linear combination of A. So the solution exists. But for it to be unique, I have to say that the columns of A are linearly independent. Now we know how to do that. We did that here. We looked at very big matrices, and we could find out how to find if columns of A are linearly independent. And you look at, if you do it in this formulation, whether you're essentially doing the LU factorization of this term anyway, so you can just look at the first part of the problem, and you'll know. So if all the columns of A are linearly independent, what does that mean? Well, that means that P of A transpose A equals LU, and then U has no 0 element on the diagonal. Right? So if this is the same problem that we had before and we checked for its existence of solution, can I go back and comment on its uniqueness? Well, yes, I can. I go here and I look at the diagonal elements of the U matrix, and there are 7 diagonal elements, and I look at them and I say there's none of them look like they're 0 to me. So all of the columns of A are linearly independent. So we've satisfied both conditions. Columns of A are linearly independent using the pro tip. And I've also satisfied that B is a linear combination of A using the semi-pro tip. So without doing anything extra, I can just say that AX equals B has a unique solution. And that was it. That's just how easy it is. All right, now that we're comfortable with all of this, I'm going to post the solutions online, and it is now time to move on to plotting in Julia. We worked with project 1 and we saw how cool plots can be. And let me just restart and clear all output so that it looks fancier. Looks like we're creating all of it in real time. It'll take a while. So plotting in Julia is done using a library implemented as plots.jl. It's a package called plots, and we simply just say using plots to make use of it. It's doing it. Okay. Why do we need plotting? Well, if you just look at the mathematical output of your solutions, like when we were doing project 1, if you were just computing transformations and you weren't printing out that point clouds, it would all mean nothing to you. You wouldn't be able to see what was happening. It would be very hard to understand the significance of your work. And it just wouldn't be as impressive. And a lot of the times when you're coding and it's a bigger solution, it's a bigger problem, you want to be able to see stuff to be able to debug it, which comes in really handy a lot of the times. Say if you were working on the point cloud registration problem and you want to calculate the transformation between 2 point clouds, you want to be able to see the point clouds and see what the different transformations are doing to that cloud, how you're manipulating that cloud. So it's very helpful to be able to plot stuff. Julia implements a plotting functionality using the plots.jl library. The plots.jl library isn't actually a plotting library. It is a meta package or a wrapper that runs other prevalent plotting backends in the background. But what that means for us is that when we're using Julia and we're using the plots package, we can use all these different plotting backends like matplotlib, plots.plotly, and then pyplots. You don't have to know the syntax of each and every plotting library. What you can just do is Julia will translate those instructions for you into whatever the syntax is for that library and handle that interface for you. So you don't have to worry about it. There's different ways of doing this. There's different backends, and I encourage you to go to their website. But the one that we're going to use is the GR backend, which is what we've used for project 1. It is the most commonly used backend. And it is also the default backend. Well, how do I know that? Well, let's see. If I do that and I check display plots.backend. Once it runs, once it precompiles the plots library, it's going to take a little bit of a time. We can check the backend, but before we do that, we're going to see line plots in Julia. These are the default plots. So when I say, well, x goes from minus pi to pi and then with a step of 0.1 between each point, and I define y, which is a vector the same length as x, and it applies the sine function to each element of x, which is what this dot operator is doing right here. It's going to apply the sine function to each and every element of x and create a new vector y. So when I say plot x comma y, it will automatically generate a line plot with these properties, and that's what you get. So this is the x. We're going from minus pi to pi. Minus pi is minus 3.14 something, and then pi is 3.14. And then this is the sine wave. So sine of minus pi is 0, sine of 0 is 0, stuff that you already know. Now the backend thing that I was talking about, it's going to take a while, but yep, you're using the GR backend by default, and that's what we're going to stick with. A way to specify a different backend if you wanted to. So let's say if I wanted to specify that I want to use GR, you'll see this in a lot of your homework problems. And then it'll just give, the plot will just be a GR. When you access your plot using, we're going to see how you're going to access a plot that's already there. But that's how you specify your backend. So now that we plotted the sine function, what if I wanted to plot like the cosine function in the same plot? Well, we can do it. The way that Julia interprets plots is if I give it one vector, that's one series. If I give it a second vector, that becomes a second separate series, and it's going to plot it as like it was a different variable being plotted. So let's see how you would do that. I define the same x, but this time my y, its first column is given by the sine operation on different elements of x, and the second column is given by the cosine operation applied to each element of x. If I plot it, I see that I printed out the size of y just so we know what we're working with. There's two columns, so there's y1 and y2. The sine, the first column gives you all the values of sine of x, and the second column gives you all the values of cosine of x. And then you plot those two together, and then the blue one that you see here is your sine wave, and the red one is the cosine wave. How do I know that? Well, empirically, I know that cosine of 0 is 1, and then sine of 0 is 0. But there should be a better way. Like this should say something else, right? But we'll get to it. Another way of plotting different plots together, like if you wanted to add, I already have the sine and cosine. Let's say I wanted sine x plus pi by 2. I want to make a shifted cosine wave. How would I do that? Well, I define a new vector, which is the cosine of each element of this vector, which in itself is whatever was in x, which was from minus pi to pi. This will take us from minus pi to pi. This will shift us to by pi by 2. And you go from minus pi by 2 to pi something, something. So yeah, it basically just applies cosine to this new vector. If I plot it, it will go on the same plot, and it will recognize, okay, there's a new variable y3, which is a shifted cosine wave by 90 degrees. And then this is what it looks like. Now, as we were talking about how there's ways to make our plots more legible and more appealing, and a lot of the times it's even necessary to specify things for our plots to even make sense. Like in this case, if I didn't know that these were sine and cosine waves, there's no way of me for knowing what is y1, y2, y3. So what we do is we can assign attributes to our plots. So remember, our x and y was just the sine and the cosine wave. So with this statement, what we'll be able to do is we'd be able to say, I want my lines to be thicker, so I'm going to set the line width to be 3. And I'm going to label my plot in the sense I'll tell it what is y1, and I'll tell it what is y2. So y1 for me is the sine wave, and y2 for me is the cosine wave. Now when I plot this, it looks much better. It tells me that the blue is the sine and the red is the cosine, and the plot is a little more legible, the lines are thicker, it's prettier. What other thing that I look at in most plots that I'm probably going to need is that I want to be able to label my x and y axis, and I want to be able to call my plot something. So there's a way to do that. It's called setting an x label, setting a y label, and I can also set a plot title. Now, this may be a little advanced, but what if you wanted to represent your x as like minus pi to pi? Like I know empirically, I know from my knowledge that it looks around -3, so that this value around here is somewhere near like minus pi, but I want to be able to see that if I'm writing down. So there's a way to do it. I encourage you to go through the code. It's called using LaTeX strings, which lets you, so I can describe where to put these dots, where to mark my x-axis. So I want to mark my minus pi by 2, 0, pi by 2, and pi. That's how I want to divide my axis. And then at those points, I want to see this string minus pi, this string minus pi by 2, and so on. And then this property is called xticks, which takes the range and the names like this. So when I run it, it's going to look a lot better. Once it runs, it's pre-compiling the LaTeX strings package. And there you go. So my x, there's a couple errors that I think is just, I don't have some downloads, but it wouldn't give you if you run it on a Lumi desk. But you look at that, I get minus pi by 2, 0, pi by 2, pi, instead of me guessing that that value is pi. And it's a lot more consistent. It's better for us. When you're creating plots, you want to get the best plot that you can. Another type of plots that we have been working with and what we will continue working with is scatter plots. Now, in line plots, you saw that I gave it a set of discrete x points, right? I gave it from minus pi to pi separated by 0.1 in there. But it joined those plots, and it gave us a full line. A lot of the times, it makes sense to not join these points, and I just want to see what the point data is. And for example, we looked at the point clouds. Now, I don't want to join a line through all of those points in my graph. I just really want to see the clouds. I just want to see the point and what they are. So we're going to use scatter plots. And while we're at it, I want to show you like a way of specifying like default parameters. So when I say using plots in here, I say default marker stroke width is, so when you're using scatter plots, you're going to put points, and then points are called markers. So you can specify the width of your markers, the color of your markers. I set it to auto, so like it'll self-assign it. And the transparency, I set it to be 0.8, and I say, well, skip the legend points. I just don't want to see it. But these are default, and you will see that we'll modify some of these when we're plotting stuff, and you can change them. But it's just easy if you just don't want to write this every time and there's like a set pattern that you're following. It's just easy to specify them as default. So I run this, and notice here that I have to specify a series type called scatter. Before, when we did just plot x and y, the default was just the line plot. But I want to scatter this time, so I can't just say plot x and y. I have to say that the series type is scatter. And that's the plot you get, the sine wave and the cosine wave. Now, instead of joining each of these points and giving you a line, it's showing us all the points that we have in our x and y vectors. Point to note, though, scatter is a function in itself. So I can call a function like scatter, and with the exclamation point, what I'm doing is I'm going to say, OK, make a scatter plot and access the same plot as before. And in that, add that z, which was our shifted cosine wave, and just make a scatter plot of that and put it in there. And I also will modify some of the plot properties. I'll add a label, I'll add a y label, and I'll also add a title. So let's see what that looks like. And that's it. That's all you needed to do. Subplots. All right. So when you're creating plots in Julia, well, sometimes it's easy to create plots like these. But a lot of the times you want to be able to create plots side by side, and you want to be able to make comparisons. And sometimes it just doesn't make sense. If you put a lot of data in one plot, a lot of your data gets lost. So what I'm going to do here is I'm going to plot the sine, cosine, and the tangent of x, and x is still going from minus pi to pi. On the same plot, now as you would expect, the tan x blows up at minus pi by 2 and plus pi by 2. So it'll be like a weird wave, and it might overshadow our x and y. So we know we should be using sine plots. And we'll make that clear when we run this plot. I'm going to divide my plot into 4 parts using the statement layout 2, 2. I'm going to make 4 plots. I'm going to say P1, which is plotting all 3 of them, the sine, the cosine, and the tan together. In fact, let's put a label in here, just so we know what we're talking about. And there's also tan. So this is the sine, the cosine, the tan, as you'd expect, because the tan blows up. Now I can't even see my cosine waves, but we know that they're still there, right? So in this other plot, so the better way to do it is I'm going to call it a fixed plot. And I say, all right, now I can actually see my sine and cosine waves. And I plot the x and y, and I plot my tan wave like separately so that I can actually see what's happening there. And sometimes, let's say I just wanted like a random scatter plot, where x goes from 1 to 10, and then y goes from any random number. It's 3 columns, and then 10 random numbers in those 3 columns. And I'm just going to call it a random scatter plot. It wouldn't make sense to plot it with my sine and cosine, and I have to make like a separate plot for it. So there's ways you can play around in this, and I think plotting in Julia, though it can be improved a lot, there's a lot of issues with like speed, and like 3D plotting isn't the easiest, but the basic plotting functionality is there. And hopefully in the future there's better support for it. But for our course, like we saw in Project 1, we made do with whatever was still available. Plotting library is definitely too big to be covered in 1 hour. A lot of it also depends on what you need at the time, the kind of data that you're trying to visualize. So should you ever come across a need to create a different plot, you will find different documentation options on the plots.jl library. They have ways to plot surface plots and histograms and like some very fancy stuff, which is easy to get from the documentation, but a lot of it, the basics have been covered, and that should be easy to translate. There's also a very interesting topic called recipes in Julia, where you can describe particular ways of plotting. Say, I defined a user-defined structure in Julia, which we'll talk about, and we can revisit how to write a recipe in Julia where I can just call that user-defined object, and it will have code in there to create a set of plots for that user-defined object, which is not like a default object. So I think that's pretty cool. Not a lot of other plotting functionalities always have it, and I've worked with it, and it's pretty handy. So yeah, that's it for the recitation today.